Are there any questions from Tuesday's lecture? Okay, so we're going to continue from where we left off on Tuesday, talking about modeling with state machines. But today we'll talk about hierarchy. So if you have a really large state machine that you'd like to design, it's difficult for a human to draw it out all at once. And so a natural way to organize things is to organize the state machines in some hierarchical fashion. Okay, and we'll go through one such way of doing things today. All right, so a quick recap. On Tuesday, we talked about different ways of composing two state machines. And one approach was synchronous composition. So in synchronous composition, the idea is that if you have two state machines, A and B, then the transitions in A and B occur simultaneously. And there is the environment makes a decision on when these transitions occur. That's one way to do it, or it could be time triggered. But either way, the transitions happen simultaneously. The other form of composition we looked at is called asynchronous composition, and we looked at a particular flavor of it with interleaving semantics. And the meaning here is that at any instant, either A makes a transition or B can make a transition, and the environment decides which one goes, but A and B don't make simultaneous transitions. So these are two concepts we now have in hand. So let's go back to the problem we looked at last week on Tuesday, and see if we can use these ideas of asynchronous and synchronous composition to reason about this program. So if you recall, here we have a main program and we have an interrupt service routine, an ISR, and they both share the same variable timer count, right? And the main routine wants, essentially the goal is the main function has to do something for 2 seconds and then stop, and it uses the ISR as a way of counting up to 2 seconds. But when we saw this last week, we noticed there are many situations where this code won't work, right? So now we saw that manually thinking about this, reasoning about this program can be quite hard. So ideally, we'd like to devise algorithms to do that for us. And if you have an algorithm and you give it, let's say, a state machine that models the ISR and a state machine that models the main function, okay, we'll see how to do that later, but let's just assume we have two state machines, and they are extended state machines. They share this variable timer count. Then you have to combine them in some way, right, to form the state machine for the overall program. So what form of combination should we use? Would synchronous composition work here? No, I see some head shaking. So, yeah, Nima? Okay.
So if you're synchronous, they need to happen at the same time they're happening. So you can't.
Okay. Yeah. So if we went with synchronous composition, it would mean that the state machine for the ISR and the state machine for the main function would make simultaneous transitions, right? But the semantics is that when the ISR occurs, the main function is suspended. It doesn't run, right? It doesn't do even stuttering transitions, right? And so it doesn't look like synchronous composition is the right semantics to give for this, because they're really, in many cases, there are no simultaneous transitions, right? Okay, so let's look at asynchronous semantics then, asynchronous composition then with interleaving semantics. Would that work? How many of you think asynchronous composition with interleaving semantics will work? Raise your hand. 1.5. All right. Okay. What about asynchronous composition without interleaving semantics, where you allow simultaneous transitions? Yeah. Yeah. Oren, you think it'll work? Okay. So it actually turns out that neither of these work. It's a little, with synchronous composition, it's a little easier to see because there are scenarios like we sketched out when an interrupt happens where the main function is suspended, right? And with asynchronous composition, you would think, oh, maybe that should work because the environment decides at any instant, okay, either the main function makes a transition or the environment makes a transition. But remember, when you have asynchronous composition with interleaving semantics, the choice is completely non-deterministic, right? I mean, either the main function can go or the interrupt service routine can make a transition, and which one goes is a non-deterministic choice, right? But that's not really the case here. When an interrupt occurs, the main function is suspended, period, until the ISR finishes, right? So it's, at that point, it's not the case that the main function can execute. It's just the ISR executing until it finishes. So, so the answer is you can't use either of those. But we'll see how hierarchy can then come in handy to model this program. Okay, so I want to remind you of the problem we were looking at last time. So last time we had labeled certain statements in the program, the program counter of those statements with certain alphabetical labels, right? So in this case, C was the statement after the while loop finishes in the main function. B is the statement inside the while loop or right before that executes. A is right before the condition of the while loop is checked. And then D and E are corresponding statements here. D is before you check the conditional in the ISR, and E is inside the conditional. Okay, and the question was, can the while loop terminate? Which means, assuming an interrupt can happen infinitely often, is it the case that the control flow of the program will ultimately come down to location C? Okay. So one point to note here is when we model these two as state machines, the program counter, the location in the program is going to be part of the state. Okay, so here's one way to model them as state machines. So this state machine models the interrupt service routine, the ISR, and this state machine models the main function. Okay, so let's look at the main function first. We're neglecting all the initialization code, and we start here essentially. So we say that for our purposes, let the main function start at location A, and it starts with setting timer count to 2000, and then from A it will then test the condition of the while loop, right? So it tests the condition is while timer count, so is timer count not equal to 0, and if timer count is not equal to 0, it goes to location B, right? And it runs whatever code is after location B, and then it comes back to A and tests the value of the loop condition again. Otherwise, if timer count is not equal to 0, then it goes from A to C. I'm sorry, if timer count is equal to 0, I misspoke. So if timer count is equal to 0, then the loop condition is false. It'll quit the loop and it'll go from A to C. Okay, so that's our state machine. And for the ISR, the state machine is similar. We're going to have another state to indicate that the interrupt has not occurred. So the idle state is when the ISR has not been activated. And then when an interrupt occurs, we'll model the occurrence of an interrupt with this input called assert. Okay, so up here, assert is an input to the combined system, and it's a pure signal that indicates that an interrupt has occurred. So if an interrupt occurs, it goes to location D. Okay, so we neglect that part, and we go down here, and if timer count is equal to 0, then this condition is not true. So the ISR will just return. It will go back to the idle state. On the other hand, if timer count is not equal to 0, which means this condition is true, then it goes to location C. And from location C, it goes back to D. But the action it takes is it decrements the value of timer count, right? So in going from E back to the end, it will decrement the value of timer count, and then it returns. Yeah, strictly speaking, I think there might be a bug in this picture because from E you should actually go down to the end of the function. Um, so, um, so actually, I think this edge should go all the way back to idle. Okay, but yeah.
What's the significance of the dash lines? Are they implicit transitions?
The dashed lines are implicit transitions, yes. So the dashed line going from D to idle, the meaning is that the condition is the negation of time account not equal to 0, which is time account equal to 0. Exactly. Okay. All right. So okay. So that's the state machine model, and the thing to note here is that the shared variable between both of these state machines is time account, and the output is this pure signal called return, which indicates that the ISR has returned. All right? Any questions about this model? Yeah.
When you're actually running the program, when the interrupt happens, the main program goes to idle.
Yeah, so here we're not going to model the main program making a transition to the idle state because we want to keep track of the fact that the main program stays at that program counter location, right? And so it's convenient to model it as just the main program doesn't run, right? There are no transitions happening in the main program, but the state of the main program is going to be wherever it got interrupted, which could be A or B or C. Okay, so so the question we had was, is asynchronous composition the right thing to do here? And we can actually do the asynchronous composition of these two state machines, and what we'll get is the state machine on the top right. Okay, so so the way we got that state machine is exactly the technique we used last time, which is you first take the cross product of the states of A and the states of B. Here A is the ISR and B is the main function. And then you end up with these 9 possibilities, right? 3 times 3. And then you add these transitions between the composite states based on the transitions in A and B. And what you'll see is that you have transitions like this. So here, for instance, if you have the main function is at location A and the ISR is at location D, then where the ISR is active, right? It means that the ISR is not an idle, it's active, it's at location D. But we're assuming that the main function can make a transition, right? So if you see that the transitions going from AD to BD up there, the label on the transition is timer count not equal to 0, which is the condition in the main function. And that's a transition that's happening in the main function even when the ISR is not idle, right? That's something we want to disallow. So the horizontal transitions you see in this picture from A, D to B, D, or A, D to C, D, these should be disallowed, right? And likewise, the transitions that go back. Okay, the same thing for AE to BE and the reverse transition. Okay, so the key point is that interrupts really have priority, and that if you do purely non-deterministic asynchronous composition with interleaving semantics, you can't model that. Okay, so so one thing we need here is we need to somehow model this notion of an interrupt being active versus not active. And one way we can do that is explicitly model the interrupt controller. So how the process of an interrupt getting activated. And we can do that with this 4-state machine. So we'll assume that the interrupt controller starts out in the state inactive. And when the interrupt happens, it goes to a state pending, which means there is an interrupt pending, and we might need to handle it. Now, if before you handle the interrupt, it gets deasserted, okay, and in this picture, we're modeling the fact that an interrupt can be deasserted, then you can go back to inactive. But if the interrupt is still asserted, then you handle the interrupt, and you go to the state that's labeled active, okay, this is the state in which the ISR will run. And if the ISR is done, so this is, if you think of this as the controller, which is deciding whether the main function runs or the ISR runs. Okay, so if the ISR completes, then it will generate the return signal, and this controller will go back to inactive. Okay. On the other hand, it's possible that when the ISR is running, another interrupt happens. Okay. So now, not only is the current ISR running, but you have a pending interrupt. And here there are two possibilities. One is the ISR finishes, and so then you don't go back to inactive, you go back to pending, because the current ISR finished. You service the current interrupt, but there's another interrupt you need to service, so you still have something pending. So you go back to the pending state. On the other hand, if the current ISR had higher priority, then if the interrupt that happened had higher priority than the current ISR, which is represented by this thing, okay, this current interrupt has not been, the new interrupt has not been deasserted. You go back to active, and now you execute the ISR for that new interrupt, and you return from the current interrupt. And that's one possibility. And the other possibility is that the new interrupt which came got deasserted, and so you just go back to servicing the previous one. Okay, so this is one way to model an interrupt controller. But the key idea here, for the perspective of our problem, which is can the main program get to C, is that we can now associate different states of the controller with the different pieces of code that are active in those states. So when the controller is in either state inactive or state pending, then the ISR is not running. The code that is running in those two states is the main function code. Okay? And when the controller is in the state active, or it's in the state active and pending, then it's the ISR code that's running, the main function is not running. Okay? So this is one way to separate out the issue we had last time, that the main function and the ISR cannot run together, right? And really the interrupt controller is what decides which code runs when. Okay? So is this picture a state machine? Is it a valid state machine? Not quite, right? Because it has code associated with states, right? So this is not the syntax of a state machine, because you have these little boxes which say this is the code that runs when I'm in pending. But that's just a C code syntax, right? You're not describing the state machine. So what you have here, this C code, is something we'll call a refinement of a state. You have a top-level state machine, which is modeling the interrupt controller, but every state of that state machine, every bubble, internally has a little state machine inside it. And that state machine is called a refinement. Okay? We've actually already seen the notion of a refinement before in an earlier lecture. Okay? Where did we see that? It was a different kind of refinement, but it was a refinement nonetheless. The hint is that it was last week. Yeah, Rafael. Sorry? The actor model? Not really. I mean, the actor model, we didn't see a state machine with refinements of states, right? But last week we did see an example of this. Hybrid automata, timed automata, right? You have a state, you have a bubble, and inside it you have differential equations which are describing continuous state, right? That's a form of a refinement. Okay, you have an outer state machine, but inside every state you have a different system. It's not a discrete system, it's not a finite state machine, but it's a continuous system that's defined by a system of differential equations. Okay, so that's what we're going to talk about now in the next several slides. So I will come back to this picture, the problem of the interrupt service routine and the main function, once we have gone through some basics of hierarchical state machines. So for hierarchical state machines, the picture is as follows. You have a top-level state machine, like this one, and it has, in this case, you have two bubbles, A and B. And you go from A to B when guard G2 is true, and you do action A2. and from B to A, it's G1 and A1. But inside B, you have a refinement. You have another state machine that runs when you're in state B. Okay, and so B is called an OR state, because when you're in state B, it means you're in one of the states in the refinement. Okay, you're either in state C or you're in state D. And C and D have a similar picture, right? There's a guard and there are associated actions. So what becomes tricky with hierarchical state machines is when do transitions happen, right? Because you have a state machine inside another state machine, and let's say you're in state B, which means you're either in C or D, and guard G1 becomes true, and let's say when you're in B, you're actually in state C, so G4 also becomes true. So you're in a situation where G1 is true and G4 is true. Okay, and so if G4 is true, you're enabled to go from C to D, and if G1 is true, you go from B to A, which means you exit this state machine, right? So then there is this question of which transition happens first, right? If the transition from B to A happens first, then does that preempt this thing? Like, does the transition labeled with G4 occur at all? And the reason this question is important is because you have associated actions. So let's say A4 is modeling an assignment to some variable. And if you don't take that transition from C to D, then A4 doesn't happen, right? And so that assignment doesn't happen. So you need to assign proper semantics to what happens, which transition runs first, and what happens to actions in the refinements. And there are many variants. Different groups and different people assign semantics based on what works for them. What we found useful is to work your way bottom up, so to speak. So what you do is you first say that the refinement reacts, and then so the refinement would go from C to D and generate action A4. And then you say that the top level function reacts, and G1 is also true, so this transition happens. So think of it as a sequence of statements, just as you would write a program. So you first execute the transition in the refinement, then you execute the transition in the top level state machine. And what happens is you end up in state A, and you do both actions. You do A4 and then you do A1. Okay? So you can visualize that in the form of the trace of the state machine. So let's say the state machine starts off in A, and guard G2 is true. It generates action A2, and it goes to B. But inside B, the starting state is C, so it's going to enter state C. And then in state C, let's say G4 is true, so it goes to D. And then from D, let's say G1 is true, so it goes back to A. All right. So now this is a different situation from what we discussed in the previous slide. So we are assuming G4 and G1 so far are not simultaneously true. So now you're in state A, and again from state A, G2 is again true, so you go back to B, but this time you enter in the state in which B was the last time you left it. Okay? So here, when you went from A to B, you actually entered the initial state C, but the same condition, you go from A to B, you enter the state in which B was the last time you left it. Okay? This is known as a history transition, the fact that there is some state inside the state machine which keeps track of where you were the last time you left it. Why might this be useful in the context of our example? Yeah? You need to resume where you left off. So think of the main function, right? The main function is a refinement. And let's say you go back in the controller state machine, you go back from active to inactive. And the inactive state has a refinement, which is the state machine of the main function. And you have to go back and restart at the program counter location in which you were suspended, right? So that's why history is a useful modeling tool. And this is an example of what I talked about earlier. This is a transition where both G3 and G1 are true. So you're in D, G3 is true, so you can go back to C. However, the outer guard is also true. So the ultimate result is you make a transition from D to A, but you do both actions. You first do action A3 and then you do action A1. Yeah.
Does that imply if you go from A to B again, then you go back to C?
Okay, so in this case, yeah, that's a good question. So in this case, the meaning here is that this transition happens, right? And so you internally the state machine has made a transition to C, but then the outer state had its outgoing edge as a transition also true. So you left B to A, but when you left B, you were in state C. So when you go back, the history would indicate that you end up in state C.
Why can't you just model that as a sequential thing instead of simultaneous?
Yeah, so it's a good question. So the question is, why can't you just model it as D going to C, C going to A, right? Because that's really what's going on here. If you flatten the state machine, that's what you would get. Okay, so basically this modeling aid of having a refinement of a state machine, it's a convenience, right? It was introduced mainly because if you're a human designer and you're creating a state machine in a tool like LabVIEW, right? You can't really draw large state machines all at once flat. You can't. It's going to be hard to draw something like that. But it's easy to draw refinements. It's very natural, right? Because you say, okay, there's a top-level interrupt controller, and then in these two states, this happens. In these two states, this other thing happens. But the real state machine is this one. It's a flattened state machine, okay? And now if you follow the transitions in the flattened state machine, they're exactly the transitions that you would have in this trace that we just had on the previous slide, okay? So so here, for instance, these two bubbles, the ones with A's in them, they really represent state A, but they're representing state A with the additional history information, which is when I entered state A, I came from the state where C is active, or in the bottom case, when I entered state A, I came from the state where D was active, right? And then these two are simply C and D, the two states C and D, okay? And so this transition going from D to A when G3 and G1 are both true, this is effectively modeled like this, right? This is this transition in the flattened state machine. But remember, it goes back to state AC rather than AD, right? And that's modeling the fact that the internal transition happened from D to C. Okay, question?
What happens if you're in state A in top level and
Yeah, so the question is what happens if you're actually in state A, which is this one, and yeah, and G4 gets true. So what should happen is that there should be no transition. You should continue staying in the state A, because the active state is A, right? So B is not active, and therefore the transitions out of B are not active. You're not checking for those guards, right?
I got this one. So if you're in state A, C,
Correct.
and then G4 becomes true,
Right.
shouldn't you go to state AD?
No, because the refinement of state B is not running. It's not executing, and therefore even if guard G4 became true, yeah. So it's actually tricky here. This is not concurrent composition. You're not running these two simultaneously, right? This state machine CD is not really running simultaneously concurrently with state A.
I guess I wasn't sure if the CD machine was also in state A.
Yeah. So again, I think this hierarchical notation is again the main use is it's easy to create models like this, but you should be aware that it really represents sequential behavior. There is no concurrency in this picture, okay? And so when you're in this state, essentially you're in state A, and only the guards that are outgoing from A will be evaluated. Okay? Questions about this? All right, so the whole issue of dealing with hierarchy and state machines is pretty tricky. So we all get tripped up all the time. So if you have questions, even later on, we can go back and look at these concepts. Now, one of the things that makes it even trickier is that not everybody likes this notion of history, right? So when I left the refinement of state B, I mean, there could be a case where you don't want to come back to this last state that you left. For instance, when you execute an ISR, you always execute the ISR at the beginning, right? You don't go back and resume it at some other point unless the ISR itself was interrupted, right? But if it's a new execution of the ISR, you start at the beginning. So this, suppose you want to model this, then in notation-wise, we use this slightly different arrow to indicate that. Okay, what this arrow says is, when I go from A to B, whenever I enter B, I'm going to start in state C, no matter what state I left it in. Okay, so this is like when I execute the refinement of B, I'm always going to reset that state machine back to the initial state. So here, if you see this transition, so you go from A to B, and you enter in the initial state C, and then you go from C to D, and then from D you go back to A. Okay, so you were in state D, but G1 became true, so you go back to A. And now if you go back to A to B, from A to B, you won't enter into the state D, which was the last state that you were in the refinement B. You will go back and reset the state machine to be in state C. Okay, so this transition is a reset transition. This is an alternative. So you can either model a state machine using a history, model a transition to a refinement state machine using a history transition, like we had in the previous example, or a reset transition like you have in this example. Is there a question?
The reset transition is easier to flatten.
The reset transition is easier to flatten. Why do you say that? Easier in what sense?
You don't need to store history.
You don't need to store history, yeah. Good point. So for the reset transition, you don't need an additional state bit here to indicate whether or not you were in C or D the last time you were in that refinement, right? So it's easier in the sense that you have less state, right? So if you actually construct the state machine with reset transitions, in this case, the flattened state machine has only 3 states, whereas in the previous example, we had 4 states, right? Because we had this additional bit to remember of, when we go back to A, were we in C the last time we came back to A, or were we in D the last time we came back to A? Okay, and so this state machine just has 3 states, and the transitions are constructed the same way. You consider all possible combinations of the guards. Okay, so now we've talked about hierarchical state machines with history and with resets. There's one more notational detail here, which is the notion of preemption. So if you look at this picture over here, you'll see that this transition has a little red dot at the beginning of the transition. What it means is that this transition can preempt anything that's going down in the refinement, right? So here, if you're executing machine A, and let's say you're in C and G4 is true, and G1 is also simultaneously true, then G1 takes precedence. Okay, so then you go from B to A, and you do not execute anything in C. So here, the state machine becomes even simpler in the sense it has fewer transitions, right? So the picture is less cluttered. So here, what happens is, if you were in the refinement of B, which is the 2 states C and D, and if guard G1 became true, then you would go straight back to A. Okay, same way, if you were in C and G1 became true, you would go straight back to A. You will not execute any of the actions inside the refinement. Okay, and here, to make it explicit, you have to say, okay, if you're inside the refinement and G1 is not true, that's the only case when you make the internal transitions. Okay? Why would you need this new notation, preemptive transitions? Where is it useful? Yes?
Maybe if you want to stop something like immediately.
Okay, sure. So it's useful in the setting of interrupts, right? So let's say in the main function you were about to execute, let's say, part of the code in B inside the while loop, and let's say that was just incrementing some counter, some local counter, okay, and in the and the interrupt happened at the same time, okay. So if the semantics is that the main function is immediately suspended, it doesn't actually execute this piece of code, then even though the two transitions were enabled, you don't take both of them. You don't execute the main function transition before the ISR runs. The ISR runs right away, and the main transition is preempted. Okay? Is there a question?
Is this what we would use if we had interrupts with different priorities?
That's a good question. So the question is, what happens if you have interrupts with different priorities? And yes, you would, right? So if you had the ISR, and then you had another ISR2 for a different interrupt with a higher priority, and if the ISR is interrupted by this higher priority interrupt, then you would stop. You wouldn't execute anything in the ISR. You would immediately jump to ISR2 and execute that. Okay. So let's go back to this example that we had, right? So we had this interrupt controller with 4 states. Now, it's a little bit more complicated to reason about the 4-state interrupt controller. So we're going to look at a simpler version. So here we have a 2-state interrupt controller, and the starting state is when the ISR is inactive. So the main function is running, and this state is when the ISR is active. And when an interrupt occurs, which is you get the assert input, then immediately you preempt whatever's running here, and you go to the active state. And when you're in the active state and the ISR finishes, then it generates the return signal, and on the return signal you go back to the inactive state. Yeah. Yeah. So good point. So the point is that we want to keep track of history, and the default is history, right? So here, when we have these solid arrows, then it means that any transition into the refinements will be to the last state of that refinement, right? So history is the default case. Sometimes people make it explicit, so they have a transition and they write a H or something like that, or the state or the modeling tool inside whatever you're using, like LabVIEW, which by the way it has this feature of modeling with hierarchical state machines. So there will be some explicit notation which says, oh, this is a history transition, right? Right. So you have to understand what's the default semantics in whatever modeling tool you use. Sorry, what does that bubble mean? Yeah. So the bubble is actually a state of the controller which has an associated refinement. So in this case, the inactive bubble. Oh, the red bubble. Yeah, there are too many bubbles in this picture. So the red bubble means that this is a preemptive transition. Okay. Okay. So when you're in the inactive mode, you're running the main function, and when you're in the active mode, you're running the ISR, right? So effectively, what we have is this state machine. Right? This is really a hierarchical state machine. We have 2 modes, inactive and active. And in the inactive mode, we're actually running the state machine of the main function, okay, this one. And in the active mode, we're running the state machine of the ISR. Okay. Now, one of the things in this model is that we assume that in the ISR, interrupts are disabled. Because as you'll note here, in the ISR state machine, it doesn't really check for any new interrupts happening, right? So it's not really, this model is not keeping track of the fact that there could be another interrupt with a higher priority that could preempt the ISR, for example.
Why is the error this time like the
Yeah, so, okay. So, oh, I see. So this arrow here is a reset transition. Yeah, okay, good point. So that was probably an error in the first place, right? So when we go from the main function to the ISR, we always have to start at the initial state of the ISR, right? So that should have been a reset transition from the first place. So we should actually go and fix that slide, the previous slide. Okay? So it makes sense for this transition to be a reset transition. But when you go back to the main function, you want to resume wherever you left off. Okay, so now we have a model of the program that we started out with, right? And the goal was, for this state machine, can you reason about whether you will finally end up in C? Okay? All right, so then what we internally do is we create this composite state machine. Okay? So I think in this case it would be instructive to actually work this out and see how this product is constructed. So so the way you do this is you start with the initial state, right? And you start in the inactive mode, which is going to be the main function is in A, and the interrupt service routine is in D, right? And in this case, we are modeling the interrupt service routine to start off in D. And then the initialization is that timer count is set to 2000. And then what happens next depends on whether assert is present or not, right? So assert is the top level preemptive transition. So if you get an assert, then it means that so anything inside the state machine for the main function will not execute, right? So if you get an assert, then you go from you don't want to start in D, I think, for this. You should probably start in idle, right? Yeah, that's a good point. So you want to what we really should have we should have in this is an idle state which reflects the fact that the interrupt service routine is not active. Let me just denote it by this idle, okay, symbol, which says that A, you're in mode inactive, and the ISR is idle. And so now you make a transition from idle to D, and D is the initial state. So you've taken care of the reset. Okay, and now that you're in the ISR, one possibility is to go from D to AE, and that will happen when timer count is not equal to 0. Right? And the other possibility is you go from AE back to AD. And decrement timer count and generate the return signal. And when you generate the return signal, you should be going back to location A and idle. Okay. All right. So that's one loop. The other possibility is that you were in A idle and there was no interrupt. So you check that transition. So is timer count not equal to 0? And this would go to B comma idle. Or you have another possibility, which is timer count is equal to 0. Okay, let's just do that. So you go from A idle to C idle. Okay. And then what happens in B idle is symmetric to this case, right? So you could be in the main function, you could be at location B, and an assert happens, and you end up in B comma D, and then you have the same kind of behavior here, okay, with the same labels. I'm sorry? B idle, oh yes, there's a back transition from B idle to A idle, right? Corresponding to that unlabeled transition from B to A. And then again in C idle, you could still get an interrupt. So you could go to CD and from there to CE. Okay, and that would be exactly, the labels would be symmetric to what we had for A and B. So I think that does it. All right. Okay, so that's how we get this example. So here, of course, we've represented that as inactive, as being an A and inactive. So now, if we want to reason about whether the location C is reached, okay, that corresponds to checking if C comma idle, or what's on this slide is called C comma inactive. Can you reach that mode or any of the other modes with C in them? Okay, can you reach one of those states? And so certainly there is one path to reach it, right? So you can certainly go from A idle to C idle directly, or you can take a bunch of transitions and ultimately take the transition from A idle to C idle. But the problem is that you also have many other loops in the state machine that could be executed infinitely, right? So so here, for instance, you have, I'll get to you. So you have this loop here from A inactive, and the interrupt is asserted. It goes to this the ISR invocation, and then comes back to A inactive. And it's possible for an interrupt to happen. It's unlikely, but it's certainly possible for you to get an unbounded number of interrupts when you're just at location A. Okay? Yeah.
If we had the history, we kept the history, then we didn't have that.
Okay, so the question is, we have history in going back to from ISR back to main, right? And the question is, if we didn't have history, should we maintain idle?
No, since we don't have history when we go to the interrupt, so
When we go to the interrupt, yeah.
like when we are going from like inactive to active,
Right,
since we reset the whole thing,
right.
that's why we have idle. Otherwise, we kept the state that the active state has, and that's kind of like.
No, I think the problem is that if you looked at our original model of the ISR, we actually had an idle state, and in this picture, that's missing, right? So if in the interrupt service routine you started off in the idle state, and then you have this immediate transition, which will be executed when you have an assert, right? Now, the sort of the minor subtlety there is that if, let's say, you went from inactive to active and assert was present, then if you had an idle state inside the box with also an assert on it, it would mean that assert has to be present in two successive steps, which is, in principle, what would happen is really there's only one interrupt assert, and you execute the transition corresponding to jumping to the ISR and also going to D all in one step, right? And so because of that, sort of it was our previous ISR model was not quite compatible with this. So here the implicit assumption here is that when you go from inactive to active, that you're essentially in the ISR, you're activating the ISR, going from idle to D, right? And then you start executing whatever is from D. Okay? Okay. So, reasoning about whether C can be reached, we see that you can actually end up in these loops, right? Either looping in between A idle, AD, and AE, or B idle, BD, and BE, and you can do that infinitely many times. And in the state machine, those behaviors are completely valid. It just corresponds to an interrupt happening infinitely many times. And if those scenarios happen, you would never reach position C.
That picture. No, AD to AD, because then you just move back and forth between those two. Because if you did AD
Yeah, that is.
to AD and then AD back to AD,
Uh-huh.
it would check the count and then it'd go back down, and so it never actually looped.
Okay, I see what's going on here. So if you look at this, so the question is that here, as opposed to what we have on the board, we have a single transition from AE to A inactive, right? Okay, and so what we have here in the picture is that we go from E to D, decrement timer count, and generate return, and that this output return is an input to the top level machine, right? And that this transition occurs instantaneously. So you generate the output signal. That output is read in the very same cycle, the very same step, and the top level refinement reacts on that and goes to inactive. Okay, so that is indeed more accurate than what I have on the board here, which is you go back to D, and there's a possibility of going back to timer count. That's right. So this this transition should be direct. And the same for the ones over here. Okay. That also brings us to another point, which is when you're in the, it brings us to this point about if you have two guards true at the same time, what happens, right? So here, this guard was true, and you generated the output signal return, and the output is generated at that same instance. It's instantaneous with that transition, and therefore that means that this outer guard, the top level guard, also becomes true right away. Okay, and so therefore in the flattened state machine you have a single transition. Okay, good observation. Yeah.
Could that sort of condition lead to sort of infinite loops within your state machine?
Yeah. Okay. All right, good. So the other observation is what happens if something here generates an output which may contradict the output of this, right? Because we are saying that both transitions are instantaneous, they're simultaneous. And this is something the designer has to be careful to avoid, right? So you have to make sure that your output actions don't contradict each other. One concrete instance of that, not exactly the scenario that you described, but one instance is you could have a variable that is updated, right? And inside the state machine, you update the variable, you set it to 0, let's say. But here, with this transition, you set it to 1 or something like that. And those two output actions would contradict each other. So you don't know. You have to assign additional semantics to say, OK, which one really is the output action that is finally made. And you can say, well, it's sequential, so the internal assignment happens first, and the outer one happens next, right? But that's just a choice that a particular modeling tool makes, right? So it could be the other way around as well. So the safest thing to do is make sure that the variables that are updated inside the refinement are not the same variables that you update on outgoing transitions from that top-level machine. Okay, so although we talked about this scenario, I think, in class last time, so this is what happens when an interrupt happens infinitely many times when you're at the same location in the main function. We said it's unlikely because the time between interrupts is likely to be larger than the time it takes to execute a piece of code, like check the conditional of the while loop, right? So that was one scenario. The second scenario we discussed in class last time is this one. So suppose you assume that interrupts are not disabled in the ISR. Then let's say the ISR was executing. It could get interrupted by itself, right? So you have another copy of the ISR that starts running. And this could happen ad infinitum, right? Or we also talked about the case where, OK, maybe interrupts are disabled, but just after you've disabled interrupts and before you execute the return, this ISR gets interrupted by itself, and then another copy starts running. So this model of the ISR cannot capture that scenario because we're assuming that only one copy of the ISR can be running, and this ISR cannot be interrupted by itself. So here's an alternative model that we have. So here you have the original ISR, right? And then this ISR in turn can get interrupted. So you have this other input symbol interrupt, which in this case we have only drawn for the state E, but you could have it in any state of the ISR. And if you get the interrupt, then you go to another copy of the ISR state machine, right? The second copy has states D2 and E2. And that second copy can get interrupted in turn, and then that would go to another state machine, D3, E3, and this could keep going, right? So now, if this was our model, first of all, is this a finite state machine model? No, right? Because you have this dot, dot, dot. You have an unbounded number of, an unbounded chain of these state machines, right? So it's not really even a finite state machine model. But let's assume that we have, it's a form of an extended state machine with infinitely many states. Now with this model, will C be reached? Okay, and so the answer is no. We've seen this in class last time. And the counterexample here is something that it's going to be a path in this state machine, in this graph, right? So the path in this graph that corresponds to the case where C is not reached is the path that you get by, let's say you're in A or B and you get interrupted. You start executing this ISR. So let's say you go to idle to D to E, and then you get another interrupt. So you go from E to D2. You start executing D2. And remember, timer count is still not equal to 0, right? So nothing has changed. So now you go from D2 to E2, and you get interrupted. You then start executing the third copy. And so the path that you'll follow will be the one that corresponds with all the solid edges in the top picture, right? You'll go from idle to D to E to D2 to E2, etc. Okay. So So that's all I'm going to say about this example. Are there any questions about this example? So one thing you should note here is that the property that we wanted to think about was whether you eventually reach a particular state. In this case, it was state C in the main function, right? The counterexample for something like this, let's say if you look at this slide, the counterexample to showing that C is never reached is a cycle in the graph, where you stay stuck in the cycle, and because you're stuck in that cycle, you never reach C. Okay? So the property that C is eventually reached, that's a form of property called a liveness property. Reaching C is actually is a desirable property of the machine, and you want that to be true eventually. And the way that is not true is you get stuck in some kind of a bad cycle where you're just sitting in state A and getting interrupted all the time. Okay. So now what you see here in this example is that this is really an instance of communicating state machines, where the communication was through the shared variable timer count. Right? So you had a state machine main, a state machine ISR, and they were communicating through a shared variable. Now this form of communication through shared variables is often referred to in the literature as the thread-based model. Although here there were no threads in the sense of programming with p-threads or something like that, but the model of computation is often referred to as threads communicating through shared variables. Okay, and there are many alternative models for composition. Next week, I think you'll study threads in class, and then later on in April, you'll study alternative ways of composing machines concurrently. Okay, so this notion of hierarchy, drawing state machines with hierarchy, that actually dates back about 25 years to a paper by David Harel. David Harel is a computer scientist in Israel, and he came up with this notation that he called state charts. So state charts, in principle, they look like the hierarchical state machines that we have, but they're a little bit more expressive than that. So what we've seen today is mostly drawing hierarchical state machines with OR states. Right? OR states are like the states like B, where inside B you could be either in C or in D. Right? But like I reasoned about, you really didn't have concurrency there. You didn't have the ability to be in executing two state machines at once, so either physically simultaneously or logically simultaneously. But in many systems, you actually do have that. So here's an example, a little toy example of a state chart, which models a television controller. So the TV starts off in standby, and these labels are interchanged. So it should be, when you get the on signal, it goes to the on mode, and then this big outermost rectangle is representing one superstate, and this superstate is something called an AND state. So an AND state is denoted by splitting the box with this dashed line. It means that there are two concurrent tasks running. When the TV is on, there are two concurrent tasks running. One handles the image, and the other handles sound. Okay, and it makes sense. You would have you want these two to happen at the same time. So either physically or logically, you want two tasks to be running simultaneously. And in the sound controller, it starts off mute, and if you turn on the sound, then it goes to the on mode. When you hit mute, it goes back to mute. And note that inside, this is like a state it's like a refinement, right? So the sound is like a big state, and inside that state, you have a refinement which comprises these two state machines. And then in the image mode, you start off with a normal image, but then if you press text, you get to a closed caption mode, and then you toggle that, you go back to the normal mode, right? So this sort of diagram is more common. So if you use LabVIEW, for instance, has a state charts a model of computation that you can use to model systems. and you can draw diagrams like this. One thing that's not explicit here is how you communicate between these two state machines. So for instance, if I'm in the on mode, then both the image task and the sound task are running at the same time, correct? So now if I get the off signal, you simultaneously quit both modes, right? And you go to standby. These two modes might share some variables, but also the communication between these two modes is the communication in the state machine is one mode is to do broadcast. So broadcast is, let's say, if these are all implemented as digital circuits, for instance, you could have two chips that one of which is dealing with the image and the other is dealing with sound, and they're both on a bus, right? And when a message has to be sent to both, you broadcast it on the bus, and both of them receive the message. So that's a way of implementing broadcast communication. So in state charts, in the hierarchical machines we have seen so far, the communication has been through shared variables. You don't have broadcast and other mechanisms. But when you use commercial tools for modeling with hierarchy, then you have additional forms of communication that include broadcast and also point-to-point messages. Okay, so that brings us to the end of the lecture. So yeah, Nima, you have a question? Okay.
The transitions that we have over there, like if we have third and time counters, we call it zero. Which one do we take?
So
Same time. If you're checking that condition and we have this third, don't we need to have the counters zero?
oh, I see. So the question is, what happens if you're an A idle, for instance, and assert is true and timer count is not equal to 0, right? So in this picture, assert is a preemptive transition. The transition labeled with assert is a preemptive transition. So you can only go from A idle to B idle when assert is not present, right? And so effectively there should be a label which says not assert here. Yeah.
So we do need to split that later or no?
No, I think we should. So we've been a little bit sloppy here with the notation, even on this slide. Right. Okay. So to summarize, in the last class we talked about composition, right? Different ways of connecting actor models together, and you have syntactic composition, connecting in series or parallel or with feedback, and then you have semantic composition, which is synchronous, asynchronous. And today we talked about hierarchical state machines, which is a way of not doing concurrent composition, but you just can build a more complex state machine by having refinements with individual states. And in order to actually check if some property is true or not true, you have to flatten this. You have to flatten the hierarchical state machine, and you have to take the composition, the cross product. But fortunately, there are tools that do these things for us today. So we'll study about these tools in a technique called model checking in April. But for modeling for the human front end, it's convenient to have these ways of composing machines and using hierarchy. All right. Any questions about this stuff? Okay. So keep in mind these topics. We're going to, when we talk about threads and scheduling and so forth, we're going to be using state machine models quite extensively throughout.